Good evening, Chem Kids. I'm going to review with you how to name acids and how to do pH problems and how to use the Ka table. I'm going to use the review that we did in class, and I'm going to choose certain parts of it that I think could be the most confusing. Let's start with naming acids. When you name acids, the most important thing to look at is whether the acid is binary, which means two elements, H and something else, or ternary. The ternary are also called oxyacids, and it usually involves hydrogen, another element, and then some kind of oxygen. So 1, 2, 3. Number 11, for example, is a binary acid, and because it's a binary acids get named with the rule hydro, root word, and then the ending IC. So in the case of HI, it's binary, so we're going to name it hydro, root word IOD from iodine, and then we're going to give it the ending IC, and then we're going to add the word acid, so hydroiodic acid. Number 14 is working backwards. It starts with the word hydro, so we know that we're looking at a binary acid that has the root word brom. We go to the periodic table and we see that that could only be bromine. Bromine has a charge of -1, so we add hydrogen to that, and we make our formula HBr. This next problem is a little different. It's not a binary acid. It is a ternary acid, 1, 2, 3. There's our hydrogen and another element, nitrogen, and then there's our oxygen. And the key to those are to look for a polyatomic ion. And in this case, I hope you can see that the polyatomic ion is nitrate. Since the polyatomic ion ends in ATE, the rule is that then the acid will change that ATE suffix to IC. Things that end in ATE get the suffix IC. They do not use the word nitro, and so the name for this acid is going to be nitric acid. Not hydronitric, but just nitric. The next one is carbonic acid. We're working backwards. And if you notice, carbonic acid does not have the word hydro. And so it has an IC ending, so we know it comes from a polyatomic ion that ends in 8. The root word is carbon, so we're looking for carbonate. The carbonate ion. And the carbonate ion has a charge of -2, so that means that we need 2 hydrogens in order to cancel out the -2 charge, and so we get the formula H2CO3. This next acid is another ternary acid, 1, 2, 3, or oxyacid. So therefore, we look for the polyatomic ion, which I hope you can see is PO4. That's phosphate. Phosphate ends in 8. That means that this acid is going to be phosphoric acid. And our last one, sulfuric. Sulfuric, again, no hydro, ends in IC. That means we're looking for sulfate. And sulfate has a formula of SO42 negative. We need 2 hydrogens. to balance that out, and so we get the formula H2SO4. One more example. If it was sulfurous acid, we would be looking for the polyatomic ion that ends in sulfite, and that is SO3, 2 negative. Adding the 2 hydrogens, we get H2SO3. So to summarize, naming acids, binary acids get root word, hydro in the beginning, root word, and then ic. And then ternary acids, also known as oxyacids, look for the polyatomic ion. Look for a polyatomic ion, and you will have the polyatomic ion list. If the polyatomic ion ends in 8, the acid will end in, the acid name will end in IC. If the polyatomic ion ends in ite, then the acid name will end in OUS. All right, we're now ready to do some pH problems. Again, you will have the formulas for pH. The first problem is, what is the pH of a hydrogen ion concentration of 3.5 times 10 to the minus 4? Okay, remember that the brackets mean molarity. The brackets are a unit of concentration, and the unit is molarity. So we're going to use the formula pH equals negative log of the hydrogen ion. That formula will be given to you. So as you can see, they're giving you the hydrogen ion. So we're going to put that number 3.5 times 10 to the minus 4 in the brackets. And I'm going to take the log of 3.5 times 10 to the minus 4, the negative log, and I'm going to get a pH of 3.5. Now in class we said that was a coincidence. It happens to be the same number of the concentration, but that doesn't always happen. The pH for this problem, the answer is 3.5. Okay, these next problems are a real joy, because these are, and there's some of these on the test, when they ask you for pH and they give you the pOH, or like the next problem, when they are asking for the pOH and they give you the pH. And the wonderful formula for this is that the pH plus the pOH equals 14, and this is also a formula that you have on the back of your periodic tables in class. So they're giving us the pOH. I'm looking for the pH. So pH plus 3.10 equals 14. And as you can see, what we have to do is we have to subtract 14 minus 3.10. And 14 minus 3.10 is 10.9. The next question is whether that answer is acidic or basic. Remember, the pH scale goes from 0 to 14, so anything above 7, like 10.9, is a base. The next problem is very similar, except that they give you the pH. The formula is still the same, pH plus pOH equals 14. This time they're giving you the pH, so 9 plus 4 plus pOH equals 14. To solve, we have to say 14 minus 9.4. So let me write this another way. Okay. POH equals 14 minus 9.4. And 14 minus 9.4 is 4.6. So our POH is 4.6. Now you would think that this is acidic, but it isn't, because this isn't a pH, this is a POH, and we have to decide on whether something is acidic or basic based on the pH right here. So the pH is 9.4, so this is basic. This next problem allows us to go a little deeper into the formula. We use the formula pH equals negative log of the H plus concentration, except this time they're giving us the pH. The pH is 8.6 equals negative log of the hydrogen ion. What you want to do is transfer the negative over to the other side, and we get negative 8.6 equals log of hydrogen. And as we talked about in class, we can't divide out by log because log is not a number. Log is a process. So you have to do the anti-process to get rid of the process. So in order to get rid of a log, you have to take the anti-log of negative 8.6. If you go to your log key on your calculator, above it that you can reach with the shift key is 10 to the x. So basically what you're doing is you're taking 10 to the negative 8.6. And that is also called taking the anti-log of negative 8.6. You're raising 10 to the negative 8.6 power. When you do that, you're going to get an answer of 2.5 times 10 to the negative 9. And since you're looking for concentration, then your unit is molarity. So this is your final answer, 2.5 times 10 to the minus 9. And again, you got that by taking the anti-log of negative 8.6 or raising 10 to the negative 8.6 power. Now we're going to do a little bit of Bronsted-Lowry problems. And the most important thing for Bronsted-Lowry is that you connect the right things. So remember, you're going to basically look either before or after the arrow, and you're going to connect the things that are the most, what we call structurally similar. And that would be NH3 and NH4 plus. And we can see that the NH3 became NH4 plus by accepting a hydrogen ion, and that is what is defined as a Bronsted-Lowry base. So this is a Bronsted-Lowry base. Bronsted-Lowry bases are always connected to conjugate acids. So NH4 plus is the conjugate acid. Remember, bases are connected to conjugate acids. That leaves water to be connected with hydroxide ion. And if NH3 was the base, water must be the acid. And we know that it is because if you look at the OH on the other side, it seems to have donated a hydrogen ion. And so that is the acid. And remember, acids are connected to conjugate bases. So acids are connected to conjugate bases. Remember that. All right, so now we've labeled everything. And so the answer would be B, A, C, A, C, B, if you were to see it in a multiple choice. That's the base and the acid on one side, and the conjugate acid and the conjugate base on the other side. Okay, now we're going to teach you how to predict whether it's the reactants or the products that are favored in this kind of Bronsted-Lowry base reversible reaction. So I'm going to erase this so I can have some space. And I'm going to clean this up a little bit. So remember, it was base acid. And then it was conjugate acid. and conjugate base. All right, so remember this is a reversible reaction. Not all reactions are a reversible reaction. If it's a strong acid or a strong base, it's only going to have a one-way arrow, but weak acids and bases have double-headed arrows. And we say that one side is either favored or the other. By sides we mean either the reactants or the products. So that's what they're asking you, which side is going to be favored. And we can actually tell by this technique. The technique is to highlight the acids. So I'm going to highlight water and NH4+ because those are my acids. Conjugate acid and acid. I'm going to highlight those. All right, now I'm going to go to the table of Kas and I'm going to look up the value for water and NH4+, these two right here. And if you go to your table, you're going to see that the value for water is 1.0 times 10 to the minus 14. And you're going to see that the value for NH4+ is 5.6 times 10 to the minus 10. So we have two values. We have the value for water and we have value for NH4+. The thing to remember is that reactions favor the weaker species. And the reason that is because just like we had been speaking about in class about an analogy of a boxing match, the reaction or the fight is over when the last guy stays down and doesn't get up again, because if he gets up again, the fight is going to continue, the reaction is going to continue. So once you make a weak species, that species is too weak to turn around and continue the reaction going the other way. So basically what we have to decide is what number is the weaker number, 10 to the minus 14 or 10 to the minus 10. And if you're thinking it's 10 to the minus 14, you are correct. And so therefore, since 10 to the negative 14 number is on the reactant side, we say that for this problem, the reactants are favored. And the reason that that is because 10 to the 14 to the negative 14 is smaller than 10 to the negative 10. Smaller meaning the weaker number. So when you're asked to do a problem like this, connect your species, identify the Bronsted-Lowry acid-base conjugate pairs, highlight the two acids, go to the table, find the values, and pick the one that is the weaker number. Okay, I'll let you read through these answers. Let's practice some more, and let's go ahead and do some more of these Bronsted-Lowry connections. So for this one, I hope you're thinking about connecting H2SO4 and HSO4. This is the acid and this is the conjugate base because we can see that it's donated a hydrogen. And then water and hydronium ion. This is the base. It accepts a hydrogen to become H3O+. This is the conjugate acid. I'm going to highlight my acid, this one, and this one. So these are the two that I'm thinking about. And I'm going to go to my table. And I'm going to look up the value for H2SO4. If you look up the value for H2SO4, it doesn't really have a clear number. It just says that it's greater than 1. So that's what you write. And if you go down just a little bit, you'll see the value for hydronium ion, and that has a value of exactly 1. And greater than 1 is still bigger than 1. So we're going to say, if this is the reactants on this side and these are the products, we're going to say in this problem that the products are favored because technically speaking 1 is less than, because 1 is less than something that's greater than 1. Okay, we're going to do the same thing for this next one. We're going to connect NH3 and NH4 plus and water and hydronium ion. NH3 has accepted a hydrogen. That means that it's the base. This is the conjugate acid. And water is then the acid, and hydroxide ion is the conjugate base. Highlighting my two acids, this one and this one. I'm going to go to the table and I'm going to get a value for water of 1.0 times 10 to the minus 14. And I'm going to get a value for ammonium ion of 5.6 times 10 to the minus 10 from that same chart. And I can see that 10 to the minus 14, 1.0 times 10 to the minus 14 is less than 5.6 times 10 to the minus 10. So in this problem, it is the reactants that are favored. Finally, I'm going to join this last one, HPO4 with PO4, 3 negative, and water with hydronium ion. We can see that HPO4 minus 2 lost a hydrogen or donated a hydrogen to become the phosphate ion PO4 minus 3. Therefore, this is the acid and this is the conjugate base. Therefore, leaving water to be the base, and we can see that it's accepted a hydrogen to become hydronium ion, the conjugate acid. Highlighting my acids, that's HPO4 and H3O. I go to my table of values and I find that HPO4 minus 2 has a value of 2.2 times 10 to the minus 13. I'm going to write that over. 2.2 times 10 to the minus 13. And H3O plus, we saw that in another problem, H3O plus is going to have a value of 1. So these two numbers are dramatically very different. We can see that 2.2 times 10 to the minus 13 is way smaller than 1. So therefore, the reactant side is favored in this problem as well. So to summarize, connect your Bronsted-Lowry acid-base pairs, highlight the acids, look up the acids in the table, decide which one is smaller, and that is the side that it will be favored. Okay, we've reached the table, and this is a great table because it's going to allow you to do the relationships between pH, pOH, and concentrations. The easiest relationship to remember is that the pH plus the pOH equals 14. So that's how you're going to relate these two. And if they give you the pOH, then the pH here is 14 minus 4.63. And 14 minus 4.63 is 9.37. Working the other way here with 11.75, the pH plus the pOH equals 14. So therefore, the pOH is 14 minus 11.75, and 14 minus 11.75 is 2.25. Okay, let's continue here. The OH is related to the concentration of OH. These two are related, and the way they're related is that if you take the pOH, which in this case is 4.63, then the concentration of the OH equals 10 to the negative 4.63. 10 to the negative pH. Let me see if I can make that a little clearer. So you're going to raise 10 to the 4.63 power. Let me see if I can rewrite this. A little neater. 10 to the negative 4.63 power. 10 to the negative 4.63 power is 2.3 times 10 to the negative 5 molarity. The other two that have a relationship are the pH and the H. These two have a relationship. So, to get the concentration of the H plus, it's going to be 10 to the negative 9.37 power, or the antilog of negative 9.37. And that is 4.3 times 10 to the negative 10. 4.3 times 10 to the negative 10. The way you decide if it's an acid, a base, or neutral is if you remember what is happening to the pH. So we have to look at this pH. So we're looking at 9.37. That means that this is basic. And we're looking at 11.75. That means that this one is basic as well. Let's go ahead and get the OH concentration right here. The OH concentration, since we know that the POH is 2.25, we're going to bring that over, and that is 10 to the negative 2.25. And that is going to be 5.6 times 10 to the negative 3. And then we're going to hook the pH and the concentration of the H the same way. Let me do that in blue. So the concentration of the H is this 11.75, 10 to the negative 11.75. And that is 1.8 times 10 to the negative 12. 1.8 times 10 to the negative 12. The last one we have to do is this last row where they don't give you any POHs and pHs, but they do give you 5.27 times 10 to the minus 9 as the concentration of the H. And there's a very valuable formula, which is that if you multiply the concentration of the hydrogen times the concentration of the hydroxide ion, that will equal a constant, which is 1.0 times 10 to the minus 14. And they're giving me this, they're giving me the H. So if I do a little rearranging, then OH negative equals 1.0 times 10 to the minus 14 divided by the concentration of the H. But they've given us the concentration of the H. The concentration of the H happens to be 5.27 times 10 to the minus 9. So it's 1.0 times 10 to the negative 14 divided by 5.27 times 10 to the minus 9. These are molarities, so of course that's going to cancel. So basically I'm going to divide 1 exponent negative 14 divided by 5.27 exponent negative 9, and I'm going to get an answer of a hydroxide ion concentration of 1.9 times 10 to the negative 6 molarity. So I'm going to put that answer here. 1.9 times 10 to the negative 6 molarity. Now, to get the pH and the POH, I can just get the log of this. So the negative log of 1.9 times 10 to the minus 6 is 5.72. And the reason I put it here is because this was the OH. And so that's going to get me back to the POH. And if my POH is 5.72, then I know that 14 minus 5.72, because the pH and the pOH equals 14. So 14 minus 5.72 is 8.28. And now I have all my answers. This one, these. And there's one last thing we forgot to do, and that is to tell whether this last column is acidic, basic, or neutral. But remember, we said we could tell from the pH. So if the pH is 8.28, then once again, this is basic. And it turned out that all these three were basic. All right, Chem Kids, now don't forget to know the properties of acids and bases, which ones are bitter, sour, slippery, good conductors, etc. Look over your PowerPoint, look over your outline, and look over the review, including the parts that we did not do. Good luck, and I will see you tomorrow.